and we start going like this. So now in full screen, you still see this notebook, right?
Yeah, correct. Only the notebook.
Okay, thank you. Give me another second. Okay. Very nice. Yes. Okay. Like this. All right. So let us just recall what we have been talking so far. So it was rather, say, simple content. So just basics of machine learning, and so the whole task boils down to working with data, which is observed through sensors. And this data can be characterized by a set of features. Well, we normally refer to a sample of data as a feature vector. And again, listen, maybe it sounds trivial to you, but I always, well, firstly, I'm find it quite I'm using to think about data as shapes in a high-dimensional space. Secondly, it is very helpful abstraction, so to say. It's not an abstraction to understand the workings of different machine learning algorithms. So, and as with any kind of space, representation space of certain dimensionality, you can do a lot of things with it. You can work with this space with some shapes in it as they are. So trying to figure out what is going on and how to separate one shape from another shape. Or you can actually do transforms. You can do I mean, as with our three-dimensional or two-dimensional spaces, we can do projections. For example, we can take our many-dimensional space and try to project it to a lower-dimensional space. Or you can do expansion. So you can project, you can expand your space into high-dimensional spaces. Doesn't make sense. Well, yes, it does make sense. Today, towards the end, towards the end of the class, I demonstrate more concretely what I mean. But for example, down projection makes sense simply by the fact that you reduce dimensionality. And there are different ways to down project your data or transform your data to a lower dimensional space. You can do linear projection, or you can do PCAs, like so selecting, analyzing the variances, and But the point is that different methods of transforming data results in kind of modifications of your original shapes in certain way. You don't know in advance in which, and it's hard to visualize actually, so that you modify the relative distances between the points. So if you, for example, stick to Euclidean distance, or rather, maybe you can think about dot product or cosine similarity, as we talked yesterday. In either case, when you transform your data by one or another method, you change the distribution of your distance between the points, and that's what makes your data more separable, for example, by different algorithms. So again, I'm just saying that this kind of having a view of your data as many-dimensional manifold helps a lot in understanding of machine learning methods and different mechanisms of working with your data. But okay, so let's go step by step through this topic. I actually want to start with some preliminaries. For SVM. So the topic of today's class is support vector machines. Again, nowadays, when people talk about machine learning, so immediately, mentally, people jump into the domain of artificial neural networks. And however, so there have been very powerful algorithms developed 30 plus years ago, and no, that was not 30, like 20 years ago, which has rigorous mathematical apparatus. And understanding how these algorithms work help to increase your intuition about what does it mean to learn on data. What is it? And support vector machines is one of these classical algorithms with well-defined defined mathematical explanations on how learning happens. So, before introducing support vector machines, so we need to do some recollection of what's from the basic math courses, or geometry actually. So very in a fast-forward manner. So now we work in two-dimensional case. We have two variables, x1, x2. Again, I use interchangeably variables and features. So this is our feature vector. So today, when I write x, I mean in this with straight lines, I mean a vector. So this is a vector, and so the other axes with indices. So they are concrete features or coordinates of this vector. Again, so that we have introduced before. But again, so at this point, we just have a coordinate system with two coordinates, x1, x2. And what we can do here, we can draw a line. So let's draw a line. Oops. And again, so recall how this line is can be defined. So here we have our beta over here. And here we have our alpha over here. So if you remember, so this line can be defined as x2 equals alpha x1 plus beta. So free coefficient, right? But more than that, what you can do, so you can write a parametric form for a line equation, which is, so in general, a1, so the coefficient 1, x1 plus a2, x2 plus some b equals 0. So far, so good, right? So this is a line equation. Or again, so now if we go to higher dimensional spaces, so you can define, well, in that case, a plane. So you define it as sum of ai xi plus free coefficient equals 0. So that's our plane. Okay. Or the same thing, and that's what we will do later on. You can write in vector form. So you have a vector for A, so bold A, multiplied by vector X plus B. So that thing over here. So vector form. Okay. And it's next. So we have a line, but we want something extra. So again, so maybe we have, this is our x1, x2, and this is our beautiful line over here. And here we have a point P with some coordinates x1, 0, x2, 0, x2, 0. Yes. And what we want to find the distance of this point to the from this point to the line. So this distance. So and again, so you can there are different ways to derive this distance. So I will just write the final result so you can double check it elsewhere. So this distance. If you use now this parametric form for line, it takes this form. So it's modulo A1 x 1 0 plus A2 x 2 0 plus b modulo divided by square root of A1 square plus A2 2 square. And this, by the way, again, so that thing over here. So if you now connect it to vector form, so this is a norm L2 norm of vector A. Okay. So what is it we have here? We have coefficients for each coordinate in our space, and so we can, and it's a vector. So on the other hand, we have our vector, some particular vector, and we can compute the distance from this point. So from the tip of this vector. So if you start from the origin, so this is a vector, to a line defined by this equation. So quite intuitive, right? So that's school geometry. Then another thing which would be helpful, and most likely you use it a lot in your control theory and other subjects. I'm talking about optimization problems now. So specifically, I want to remind you about optimization using Lagrangian multipliers. So we take it on the next slide. So well, what is the formulation here? So Lagrangian. So you are given a function. So now so you are given a function, some function f. So given on f. You want to minimize it. So minimize f given constraints. Some constraints. G. So, for example, again, just a visual example. So minimize f 2 plus x squared plus 2y squared, 7, such that x plus y equals 1, and such that, and this is your G. So constraint. So this is constraint. And again, we will not go into details of this optimization stuff, but you construct a new function basically. So you take, and this is called Lagrangian. And this is a function of x and some alphas, coefficients. So which is f minus alpha g. And you minimize or maximize this, so depending on formulation. And again, for our matters, it's okay just to understand at this level. Then there are methods of solving these optimization problems numerically. Are we good here? So now that was the all preliminaries needed to understand SVM workings. So now we enter the machine learning domain, and again, so I want to recall on this geometric view on data. So and again, so we use this trivial two-dimensional case. So we have our features x1, x2, and we have our samples which somehow belongs to different categories. So that this is their placement on a plane, on two-dimensional plane. And we are now focusing on classification task. So that we want to create a model such that you input some x input sample feature vector x prime, and which spits out a category or a class. And that's what we did with the nearest neighbor classifier. So that's the same, exactly same formulation. And now you can also kind of reflect on this notations of positive negative class that was introduced yesterday. So maybe more verbally. So in the context of SVM, so labels are literally given by numbers. So we consider it, so the SVM is defined for binary classification case. So we have two categories. Samples of categories one of the categories is assigned value +1, and samples of the other category is assigned the number -1. And that is why this first category is called positive class, and the second category is called the negative class. So each of the sample in our case, as I said, is assigned a label. So normally, so assign label. And labels are normally, in many cases, are usually denoted as Y. Y. And so Y I could be either +1 or -1. So positive and negative. So you see, we are kind of transforming to purely kind of numerical formulation for starters. So on the one hand, we have vectors of some, certain dimensionality, and inside the vectors you have numbers, I mean numerical coordinates, and labels are also numbers. Okay, good. But now compared, yesterday we talked about memory-based classification. So we tried to place a new sample on the plane and just measure the distances. And for that we needed to keep all samples in the memory. So here we enter a domain of model-based machine learning. So we want to create a model that tells us for a given sample, it spits out a label. Okay. Now, SVM basics. So again, SVM basics. So what is support vectors in our case? So we denoted support decoded in vector machines. Well, machines is synonymous here to model. And now we need to figure out what are the support vectors. Well, vectors are simple. So these are our feature vectors, actually. So now we need to figure out what support means. And here again, so I'm saying that you need to have this intuition of cloud points in this high-dimensional spaces. So it's literally points, placed in certain shapes. So and what you do, and now think about these two categories. So these are the points which are kind of located near each other, but not, hopefully not intersecting. I mean, let's take this assumption they are not intersect. I mean, we will come to relaxing this assumption towards the end, but they are kind of separable. So you know how to separate. So what you do, you always can identify the border points, the border samples in both classes, right? Which on the one side of this point is there will be all samples of one class located, and on the other side of the other border points are samples of the other class located. And actually, these border points or border vectors are called support vectors. Support in the meaning for supporting for classification. So in this our example, for example, again, so let's remove this one for simplicity. So we have this vector as a border ones, as well as, so let me remove this one just for simplicity. And so this one, and this one, and this one. So those are support vectors, or vectors supporting class.
How do you determine which points are important?
That's what SVM do. We will come to it. That's the beauty of SVM. Vector supporting class. As I said, so SVM, it appeared just having purely geometrical interpretation of data, and understanding that, I mean, when you have this representation, that you need to find these data points that support the classes. And if you do, then you can build a model supporting class I, so which is support vectors. Maybe compared to this slide, so I want to do some change of notations. So these coefficients I will now rename to W's. So I will write it down now. So axis is okay, but now I want to rename these coefficients as W's. So let me so what was it? So we had this A1x1 plus A2x2 plus B. We change it to W1x1 plus W2x2 plus B equals 0. So AI to WI. Again, so that's a more kind of moving from geometry to kind of machine learning native notations, where these coefficients, as you can guess, would be weights of different coordinates of feature vectors that contribute to classification. So that's and this W you see everywhere in continuing towards artificial neural networks, basically. And then in vector form, then it will be a vector W and a vector X. Plus B. And actually, we can write it now that we have a sample, the ith sample. So whatever sample we take, so we put it into the model, and our model should give values greater than or equal to 1 for all samples with yi equals 1 and w x I plus b should be smaller than 1 for one I equals -1. So that's our constraint. So is it clear now, at least on the level of definition? So we have our vectors, of features describing phenomena in n-dimensional space. So they form some shapes, clustering together. Hopefully they kind of have some gap in between. And we are about to find the vectors, like, yes.
The classes or we said the larger than or equal to 1, but shouldn't is 0 since classes are the -1 and -1. 0 should be the point with what side.
So sorry, I think we can. I think it is like. Yeah. So it should be like this.
Figures should be centered around.
Yeah, it will be. Yes, let's do it. So actually, let me see. I think it makes it's. Let's leave it. No, let's leave it like this. Next one. So yeah, the model itself, what we are looking for, will be centered at 0. But we wanted to give values greater and less than plus minus 1. So and again, so that will be clear now. So you have so this is our case x1, x2. So now I just have this 2 instances. So our support vectors. So if you draw a line on touching support vectors, so then it will be characterized by as wx plus b equals minus 1. So that's the that's how we define. And wx plus b. So we just define 2 lines which are kind of strictly characterizing a positive and negative, or resulting in a positive and negative class, equals minus 1, or here. And that's totally correct. So our model, so we need to build a model, and our model should be located right in between. So this would be a model just for class 1. That would be a model for plus minus 1. We are interested in a model that goes in between the classes. And to find this model, so you so that would be our so we need to find the distance and maximize the distance d from the support vectors to this model. So this is our target model. And actually, what we do here, we do not maximize just one d. So we want to maximize the whole corridor or margin between the classes. Let's denote it as big D, which is equal to 2D. So are you with me here? So we have our support vectors, so those we want to find. And we have support vectors for one class, for another class. And we want to draw a line in between. So again, so the main assumption here is that you can draw this line. But let's assume. So actually, that's not naive assumption whatsoever. There are many classification, real classification problems which are called linear problems. So you can find a linear classifier. Moreover, I can, well, maybe I don't need to overload you with extra theory information. It can be demonstrated that on extremely high dimensional spaces. So when you well, talk about millions of dimensions, so mathematically you can show that you can build a linear classifier model for which separates any point in this high dimensional space from all other points, or any cluster of points from all other cluster of points. How practically useful is this finding is a different thing. But what I'm saying is that linear classification and linear classifiers are very practically important. Maybe again, since I drifted away a little bit, the state-of-the-art methods in machine learning include, for example, sampling a neural network, so activations of weights, sample the activations inside the neural network, a deep neural network, form a representation out of it, and then train a simpler classifier, so the linear classifier on them. So that makes the final production model is simpler, faster. And that also tells us that neural network, actually, what it does non-linear transformation of your data, such that when it is trained, so the you can build this linear classifier. And SVM is one of the linear classifiers. The rest simpler ones. Of course, you will work with it. I guess in lab 2. Nevertheless, coming back to this thing. So now connecting to our preliminaries. So this D is modulo WI X. So that is our X10 X20 X10 plus W2. Sorry, I'm here with them. We are in two-dimensional space. W2 X20 plus B, and divided by well, our square root of W1 square plus W2 square. In vector form, our D is modulo W vector of weights X feature vector plus free coefficient divided by the norm of vector of weights. Again, so the math here is quite simple. So you, in a way, and now look at the this distance equation or distance formula, and the way how we define how we define the whole problem. So, and that is where I think the beauty of SVM comes when just introducing assigning a number to positive and negative classes. So so our models or other should result in -1 or +1. So basically, which makes this modulo here 1. So this can be written further as, so that one is 1. So this D is nothing more than 1 over W. So norm. So what we and this this is allows us to formulate f. So this is the function to optimize, to optimize, or actually maximize. Which is 2 multiplied by d, which is 2 divided by norm of w. So we want to maximize this number. We don't know this d's, so that's will be just a collection of coordinates. But now we numerically want to find we want to find the support vector such that the distance between two classes is maximized. And again, for the next computational trick, so to say, is to turn maximization problem into minimization. Max into minimization. So our function becomes so this is our plus f0, so that's our f to minimize. Is 1 over d. So let me put it to f1. So we are not there yet. 1 over d, and then which is 1 over 2 multiplied by norm. And then next step is to make this optimization problem convex, so that we can definitely find minimum. I'm sorry. So turn to convex. And finally, so our function to minimize becomes 1 over 2 and square of norm. So basically, these are purely kind of numerical methods steps. The important thing is that up to here, it has really geometrical intuition. So we want to maximize the margin between two classes. So find such samples that maximize the margin. Yes. And now, when we have our function, so to maximize, to minimize, sorry. Is f, which is 1 over 2 square. But we want to minimize it, but then we need to introduce our constraints. And our constraints in general form. So we go back to this line. So the constraints should be that all samples beyond this line should have model being off. That's not correct. It's +1. So it be more than +1 and in general. So not only one, but more than one. We can allow it. And here beyond the borderline, it should be less than -1. And so if you write down these constraints, so subject to constraints. So WXI, so for any sample plus B, should be greater than 1 for positive samples for Y equals to +1, and WXI plus B should be smaller than minus, I think it should be smaller. Let it be for now. So let's check. For yi equals to -1, which can be written as well then as wx. So that this system over here of constraints can be written as yi multiplied by wx I plus b should be greater than 1. And we are interested in the border case, which is actually will become our constraint function. Yi wx I plus b equals 1. So what is going on here? So if you have negative y, yes, if you have negative y, so it will be -1. This thing will be -1. It will be 1, right? And for positive, it will be positive. So so these two equations are now written as in this form. Or actually for optimization problem, so you need to turn it, so this G should have 0 at the end, so you rewrite it as yi wxi plus b minus 1 equals 0. So now this is your G that you will be using for optimization as an optimization constraint.
Is it yi multiplied with?
Yes, it is multiplication. It is multiplication. So it's all kind of math transformations on how to turn inequalities into, this type of conditional inequalities into unit experiment form. So at the end, we want to formulate a minimization problem with constraints, which look like this. So we take our minimization function of S minus alpha G of X and this G is so we have now many G's, so as many as number of samples, which results in the following formula: f of x minus some. Oh, sorry, what is that? Some alpha I G I of x. So all samples. Shall we take a break? Maybe let's take a maybe 3-4 minutes break, so to reset ourselves a little bit. I'll just, in the meantime, rewrite the last function. So. Alpha minus okay. So I think what I will do now, I will do quite quick jump from problem formulation to problem solution. Again, not to show an intermediate steps, which is actually quite funny, quite fun to do. If you're interested if you want to verify whatever I write. So again, computations involve, gymnasium level math, I would say. But now let's actually write this Lagrangian in full. So we have we include now the function that we want to minimize. So our Lagrangian is then one over two our vector of weights squared minus. And now, so we put our constraint for each sample. So we spell out this G. So sum of alpha I, and then our G, which is Y I W X I plus B minus 1. So this is our G. Again, so for you who want to do the photo verification, so this norm over here, the squared norm. So remember, it is square root. I mean, for of sum of squares, the I squares. Is that correct? So this is a norm. Then so square. So that's the norm. Which so when you raise it to square.
Oh,
Is everything okay?
yeah.
Mm-hmm. So when you raise it to square, so you have basically sum of the I squares, and this whole thing. I mean, so this WI. So these are particular coordinates, and this whole thing is nothing more than a dot product of a vector with itself. So you can write it as in vector form as W vector multiplied by W. So this is the dot product. So coordinate-wise multiplication. But you can write it in vector form like this. Okay. So now what we do now we want to minimize this thing, but you cannot attempt to minimize it right away as is. But here we have several too many parameters to optimize. We have what do we have? So if you now look at this formula, so yi is our labels plus minus 1. xy is our samples, it's feature vectors. So these are given. So we need to optimize. So we don't know b, we don't know alpha, we don't know w. So it's quite complex optimization problem. Again, mathematically or numerical methods. What you can do, you can solve a double problem. So you first take a derivative. So partial derivatives with respect to each with respect to parameters that you want to optimize, and convert it to optimization problem with single unknown parameter. So, and that's what is done. So what you do, you convert it not to double, to dual problem. Sorry. So the next step convert L to L star dual problem. And and in the dual, if you minimize in the original case, you should maximize in the dual problem, and you maximize the dual problem. Again, I mean, the transitions of what is minimized to maximize, so maybe it's not critical to fully definitely not memorize. If you are interested, then you can to increase your understanding, you can go back to algebra and numerical methods. And to do that, so as I have already said, you should do partial derivatives. So we want to leave only these coefficients to maximize. And that's what you do. So you take partial derivative by W, by all W's, and by B. So L to L star. And for that, you take dl by d double. And this is a vector. So this is a vector. So you actually take the derivative per, so it's partial derivative per each way. And you will see it even in the backprop lecture. So I mean, you are interested in finding, well, in the other case, a gradient for each weight. So how each weight contributes to minimizing the problem. So that should be equal 0. And the same goes for dl by db. So that's a number. And it also should be equal to 0. So now I will write the final results of computation. So if you can do it yourself. So as I said, so this one is it's a square of coordinates. So and here, for example, if you open up the parentheses here, so with respect to W, so it will be a sum of alpha I, yi, and this thing. So this 3 will remain in the derivative. So that will be W. So again, this is our vector. It's all in vector form, so don't forget it. And when it is not, so it is written the indices. So the indices are indicated. So I equals 1 to n, and n is number of samples. And this is alpha I, yi, xi. And that should be equal 0. And that makes it, so you can then express W as sum alpha I, yi, x, y. And if you take this derivative, partial derivative by B, it will be minus sum alpha I, yi, and that should be equal 0. Now, that is a kind of a simplified formulation of SVM. I will not do it now, but I will just comment here. So dl by d. Let's see. So you can you can insert a restriction on how tight this margin should be. So as you can imagine now, again, so it's quite simple to imagine when you look at this graphical representation. So yes, we define the lines and such, but during the optimization process, so the line can go here, here, and then the optimization tries to feed it into the data you have. And then you can introduce an extra parameter on how well it fits, how restrictive it fits, so how well it finds this border vectors. And there is a regularization parameter, a big C. So sometimes when you read SVM, so an extra parameter is included to kind of decide how tight the margin is. And it is included. I will just show you the place where it is included. It is included here. So here, regularization. The term could be included. And it will be in form C multiplied by some unknown variables per sample. So, and the larger you put C at the end, so the tighter the margin will be. So it will, supposedly it will make less mistakes. But at the same time, it's, I mean, sometimes you want to allow some mistakes for generalization purposes. And again, so I will not show it in math, but I mean, this inclusion of this regularization parameter boils down to having to take an extra derivative. Yes.
So without the C, we always find
you don't control it basically. So it's hard to. It can be. It can be located, say, a little bit within the within classes. So the margin is wide. Yeah. So some samples can fall under the model.
Yeah. So without the C's, mathematically optimal,
but model is too relaxed. So and C with C you can force the model to be stricter. And at the end, so at this point, I mean, when you take this derivative, so it will result in a constraint on alpha, which should be between 0 and C. So this constraint actually regulates which samples to take into account when building a model. So that's if regularization is included. But yes, so now when you do all this, so after taking the derivative, so you actually come to the final problem you want to maximize. So our star, which is sum of alpha I minus 1. So you take this V and this and this result over here and put it inside this formulation. Here, well, when you open the parentheses, so you will see that a term with alpha I yi xi, which will turn to 0 due to alpha I yi, sorry, not xi, which will turn to 0. Yes, but the final Lagrangian looks like this. So 1/2, and here we have two sums, which actually comes from the step when you substitute W's to this dot product. So W is a sum, and so when you multiply to sum, so those are separate sums. So that's why we have here sums from for different indices I from 1 to n, and j from 1 to n, alpha I, yi, alpha j, yj, and then here you have xi dot xj. So this is a dot product between two vectors. So you again, it comes from this equation. So when you put it, so when you compute dot product between two w's of this kind, so it will result in two sums and different indices, and then you can just, I mean, this parenthesis, by parenthesis I just separated the separation. So a dot product between two vectors, basically. Yes.
Is it DIYI then DJYJ? Or is it two?
What? Oh, so sorry. Yeah, of course, yes. And that's it. So this one you now can solve numerically. What do you have here? You have a non-coefficients, alphas, and that's what you want to tune. So there are different methods for doing that. But what is also interesting, I mean, if you look carefully here, so you have you have here your samples, your labels, plus minus 1, but this simple equation apparently is a matrix of dot products. And what is a dot product? I mean, if you recall yesterday again, so yesterday I talked about it in the context of similarity measures. So what it tries to optimize, it tries to find such axes, but I mean, to be qualified for support vectors based somehow on relative similarity of each sample. From so if you have thousands of samples, so you kind of see which samples are similar to each other. And by the way, so if you look closer, so this is the computational bottleneck of SVM, because the more samples you have, the greater matrix you have. So you need to take all samples into account here. So this matrix is called the Gram matrix, and it used to be, I mean, one of the major bottlenecks. Now, I mean, it's not that critical. You can solve quite large matrices. But so this is what makes SVM kind of computationally heavy. But what I want to show, that is SVM. So when you solve it, so you determine these alphas, and most of alphas will be 0, very small numbers, and only a few numbers will be larger than 0. And it is exactly those vectors that become support vectors. So, so that's coming back to what you asked before. So see, I still have some time. And I want to comment on a very important thing. After solving L prime, obtain few alpha I will be greater than 0. And these are the dual coefficients of support vectors. So what you do actually, so alphas is good to have, but now we need to compute the model itself. So compute model. Model, and our model, so our model is, or let's put it M, which is Wx plus B. So we with alphas, we just obtain coefficients. But what we do, when we convert it to dual problem, so our W's are sum of y I1 to M. Alpha I, yi, xi. So that's our how we compute vector of weights. So and as for B, so and again, so that's our case. So we have classes. Oh, that was So this is our model. And B, you can compute from the constraint. So yi, you remember the constraint is Wxi plus B equals 1. And to do that, again, why I'm showing this to you, because sometimes when you read, so this step was kind of not very evident, at least when I parsed the math. So you need to get get B out of this equation, and to do that, you multiply both parts with yi. So yi, oh sorry, yi Wxi plus B equals yi, right? So that's okay. This thing, so yi is plus minus 1. So this is 1. So and that all things can boils down to xy plus b equals yi, and which makes it b equals yi minus wx I. So you first compute weights for dual coefficients for support vectors. And then for each sample and a weight vector, you compute B and you take average. And you put it in. And this is your model. So the model is, and now in the production, in the inference part, so now all this trouble, I mean, it was a long time consuming computational problem just to compute this simple model, a linear model, where you input xi and then it spits out a label for you. Beautiful. So now, but this was about binary classification. How to go about multi-class classification? Two approaches. So multi-class case. Two approaches. 1 versus 1. So you basically construct you build so you build M. So if we have M classes, multiply by M minus 1 over 2 models. And then you have a voting strategy. So for each sample, so you you fill in a table. So you have classes on so classes here, class 1, class n, and then you have models here. So it's like 1 versus class 1 versus class 2, etc. Like n class m versus class m minus 1, for example. And then so you let so for a given sample, so you run you execute m so this many models and record and put the votes. So this model said this is this, and then so you decide class by the majority votes. And the second approach is called one versus all. Versus all. So here you have m classes and m models. So you take so one class, all others are negative class. You build a model. Second class, all other classes negative. Yes. And then you take basically the largest value, the largest value. So you for a given sample, you test again the models and take the largest value. That will be the and you take the model for the class with the largest value. You take the class with the model which results in the largest value. Final comment. Unfortunately, I don't have time for a kind of in-depth discussion, but that is super interesting and very important. I will come back to it when we will do a class on distributed representation. So that kind of close to what I'm doing research on. So SVM is considered for linearly so the whole model is built on the assumption that classes are linearly separable. So you have class one class, another class, and you can build a line between them. So this is linearly separable data. But many real problems are not of this kind. Rather, so a typical example could be that one class, by some virtue, again in two-dimensional space. So samples of one class are located like this, and samples of other class are located like this, are placed like this. So definitely in this case, you cannot draw a line. So that's what to do. So this is non-linear case. And here
Kernels, remap it to higher dimensions, maybe.
Yes, that's correct. That's totally correct. So you can do transformation to a larger dimensional space, but what does it mean, transformation? Again, on kind of hand waving in a hand waving style. So these higher dimensions can appear. Where to get these higher dimensions? If you have, for example, two features, right? So you know that, I mean, you can do a projection. So you have a projection matrix, for example, and you do a projection. But projection doesn't do anything. I mean, it preserves the distances between. So you expand the dimensionality, but you didn't change anything with the data. So you need to do to find such a transformation that actually changes the relative distances. So somehow put these two classes aside. And this type of transformation, I mean, you can do by including interactions between features. So, for example, in this case, So you can, so if you have a feature, and now I'm finishing, x1, x2, you can expand it, including a third feature, for example, x1, x2, and then, for example, sum of squares of these two features. Why not? X1 square plus x2 square. So now we move to a three-dimensional case. And if you, in this toy example, this is a toy example which normally used to demonstrate this. So you have a paraboloid, this, where all the inner circles end up here, and this surrounding samples end up higher up. So suddenly you can build a plane. So in three-dimensional case, it's not a line, it's a plane. And in general, a shape of one-dimensional lower is called a hyperplane. But that's it. So you can do transformations. Then the question is, find the correct transformation. Can you do it explicitly or implicitly? What SVM does, and that's what you will work on, and that will be my last word to you. It does a so-called kernel trick. This transformation of data to higher dimensional space is called a kernel transformation. Kernel is a function that transforms data to high dimensional space by modifying the relative similarities between classes. What SVM does, it does a kernel trick because why? Because it is very computationally heavy to work with high dimensional vectors in this optimization problem. But what they do instead, they said, well, why don't we modify the values of dot product, so the similarity. So we work directly with the similarity. So what kernel trick does, so here they insert a function k. So modifying the values of dot product. And this this function they call a kernel operating on a dot product, and that's what you will work with in the lab. So if, for example, you have bad results with the linear, so normally you start with the linear classifier, SVC, so linear. And then you try non-linear cases, but you should know the difference is that they non-linearly modify the similarity between samples such that they try to build the separating plane in otherwise unseparable data. So you will play around with this, but I will come back to this figure in a couple of lectures from now. So that's it for today. See you in Zoom next time. Bye-bye.